That's good.
For our first Monday seminar of 2021, we're very happy to have Jorrit Kruthoff from Stanford, who will tell us about classical aspects of the black hole interior.
Thank you, Edward, and thank you very much for the invitation. It's a pleasure to tell you guys about my work, the work I did with some people at Stanford and elsewhere. And yes, so today I want to talk about classical aspects of the black hole interior. And this was work initiated by last April. You can see my cursor. Yeah, I think you can see my cursor. Yes. With Sean Hartnell, Alex Frankel, and Darius Shi, and 2 follow-up works, basically generalizing the setup of last April to more intricate situations. And so mostly my talk will be based on these 2 papers that I wrote with Sean, Gary, and George, and the archive numbers you can find here. All right, so the plan of today will be to discuss the black hole interior of various asymptotically ADS black holes. So these could be charged black holes. I will mostly focus on charged black holes. And part of the point will be that we're considering solutions which have a non-trivial scalar profile field on top of the geometry. So roughly the geometry that I have in mind here, I've drawn the Penrose diagram of an ADS Schwarzschild black hole. And there's a radial coordinate z, which is space-like in the exterior region and time-like in the interior. The singularity is here, space-like singularity denoted in red. And we have learned a lot of things by studying the exterior of the black hole, and very important lessons that we've learned there. And one of the place that is still sort of mysterious is the black hole interior. And you might ask, okay, why would I, in the context of the ADS-CFT correspondence, try to study this black hole interior? Because first of all, we don't have a good probe to see the physics of the interior purely in the boundary. Nevertheless, we will see that there's some interesting aspects just classically, purely from the classical equations of motion that that are interesting and intricate and worth studying. So so the reason why I would like to study these black hole interiors is, okay, of course, there's a lot of them is a lot about them is unknown, even classically and quantum mechanically, even more so. And what I would like to do today is focus on a couple of things. So the interior of a black hole is unstable, unlike the exterior. And we have a scalar field, for instance. In the exterior, you just throw in some particles and there's not much that changes. But in the interior, the scalar field can actually develop for common choices of matter fields. The scalar field will blow up close to the singularity. And furthermore, one other aspect that that will be sort of the main part of the talk is that we only know the black hole interior for certain special solutions. So, for instance, the Reisner-Nordstrom ADS black hole or the Schwarzschild ADS black hole. But what about more general solutions and more in a more generic fashion, where, say, there's scalar fields present and other matter fields? And in that case, what does the interior look like for those cases? And what I would like to focus on today is study those interiors and and this will mostly be a classical discussion. So just solve some equations of motion and study the various regimes that are present in the black hole interior. So let me first mention a little bit what I mean with more generic or non-generic solutions. So recall that non-generic solutions are basically for instance, could be the ADS-Rothschild black hole or the ADS-Reisner-Nordstrom black hole, and I've drawn here their Penrose diagrams. In my talk, I will mostly focus on these type of black holes, or charged black holes. And if there's no scalar field present, so we just have this pure ADS-Reisner-Nordstrom black hole, this geometry has an outer horizon, here depicted in blue, and it has a Cauchy horizon or inner horizon. And this Cauchy horizon, it's a sort of peculiar feature of the Einstein equations of motion, because it's a null surface beyond which we cannot evolve the Einstein equations, at least not uniquely so. And recently in a paper by Dafermos and Luc, this was shown that this indeed you could continue the Einstein equations beyond that point, but not in a unique way. So here in red, again, there's the singularities. These singularities are time-like. And so this is a very special situation, special solution to the Einstein equation. And from the dual field theory point of view, these correspond to very special states. And so the left-hand side would correspond to a thermal field double state, and the right-hand side, this ADS-Reisner-Nordstrom, would also be a thermal field double state, but then with some non-zero chemical potential for du1 global symmetry. And another way of basically saying the same thing is that in both these situations, all relevant operators have been turned to zero, be fine-tuned to zero. And of course, from an effective field theory point of view, that's a very special situation and not very generic. So this brings me also to the point in how I will approach trying to get more generic solutions. And that is actually by turning on a relevant scalar operator. And so in the boundary theory, what I will be doing is turning on a relevant operator whose dimension is less than the number of space dimensions of the boundary theory. And in that way, we will see that the bulk geometry will be more generic. The boundary state dual to that geometry is a more general thermal state. And in particular, what we will see is that when these sources are turned on, is that the Cauchy horizon, so the peculiar feature that was present for this charged black holes, it will actually get removed. And I'll prove that in various ways. And that sort of the removal of that Cauchy horizon, of course, brings about a holographic formulation of the cosmic centriship, or strong cosmic centriship, where by turning on these relevant perturbations, I can enter in a more generic solutions, and these more generic solutions turn out to have do not have these special features like a Cauchy horizon. So this motivates that notion, and of course there's some overlap between the two. They're not exactly the same as the usual strong cosmic centriship. Usually would say, okay, we have some initial data and we evolve we have some generic initial data, we evolve that, and by that evolution, we wouldn't expect any Cauchy horizons. Here, of course, the time evolution, although in the black hole interior, the radial direction becomes time-like. So again, it's a sort of a time evolution happening in the interior. And furthermore, the cases I will consider are deformations which are homogeneous and time independent on the boundary. So they're present for all time. And one of the key steps in proving or showing strong cosmic censorship or violations thereof is that perturbations do not decay too fast in the exterior. So they can build up in the interior and change the geometry. And here, of course, by turning on the deformation for all time, I'm basically simplifying the problem because they will basically not decay in the exterior.
See, for this issue of the inner horizon, the fact that the operator is relevant is not very important, right? You could have been irrelevant and you would have obtained a similar answer.
Yeah, we will see indeed that if in certain cases, it's important that it's relevant. For instance, if the scalar has a charge, if the scalar is neutral, then an irrelevant operator can also remove the irrelevant operator will also remove the Cauchy horizon. That's right. I guess for the purpose of the analysis, we chose to maintain the ADS boundary conditions, and that's why we had these relevant operators. Yeah, but yeah, we'll see also sort of an interesting feature of irrelevant perturbations if we in a couple of minutes. All right. So the plan of the talk will basically to guide you in the black hole interior for two different cases. So one case will be neutral scalars and in a charged black hole background. And we will see that there's two interesting features of the black hole interior. First, we will see that there's a regime that we call the collapse of the Einstein-Rosen bridge, in which, yeah, literally the Einstein-Rosen, any finite stretch of the Einstein-Rosen bridge gets exponentially small. And secondly, after that Einstein-Rosen bridge collapse, that the black hole interior goes to a Kasner universe. And I'll explain in more detail what the metric and so forth are of this Kasner universe. And then in the second part will be about charged scalars in a charged black hole background. And there again will be a collapse of an Einstein-Rosen bridge. But the case that we will be studying is on the dual field theory side as a holographic superconductor. And so there's also a regime after the collapse of the Einstein-Rosen bridge, which are certain oscillations in the scalar field that you can view as analogous to the Josephson oscillations present in a superconductor. And after these Josephson oscillations, the geometry again goes to a Kasner universe, but then sort of a very interesting, very intricate interior dynamic starts to develop where the geometry can go from a Kasner universe to a Kasner universe with a different set of exponents, which we call a Kasner inversion. And so there can be certain transitions to different Kasner universes throughout the evolution inside the black hole. And we will see that this depends very, very sensitively on the temperature. And even in such a way that there can be many of these Kasner inversions, many transitions to different Kasner universes. And in that regime, we will even see some sort of fractal behavior that we find very surprising, very interesting, and that's something that I will discuss later. All right, let's get to the more general setup. Please interrupt if there's more questions. So the general setup that I will be considering is a 4-dimensional geometry. So we'll be working exclusively in 4 dimensions. This will also work in higher dimensions, but this is the case that we focused on. There's the Einstein-Hilbert term with cosmological constant. Then there's the Maxwell field. Then here we have the scalar field kinetic term and then a potential term. And here generically what we will consider is the mass being negative, the mass square being negative, but still above the F bound. So these are fine scalar field profiles. And in the 2 cases that we'll consider, either this is just the usual covariant derivative with respect to the geometry, or there is an additional piece coming from the charge of the scalar. And what we will do is just solve these equations, solve the equations of motion, and we'll do that in a particular metric ansatz. And the metric ansatz that we'll be choosing is this one. So there's a 1 over z square here up front. There's this function f and chi, and the planar, the transverse directions will just be a planar topology. Now in these Poincaré type coordinates, the ADS boundary is at z is 0, and the singularity will be at z is infinity. Now the horizons are the zeros of this function f, and usually what I'll denote with z sub h is the outer horizon. And that one will always be present, but we will see that the interior, the inner horizon is generically removed. The temperature of these black hole solutions, that we will focus on is given by this formula. And close to the boundary, the scalar field has this particular behavior. So there's a source term here, and there is the expectation value of the scalar field. We will sometimes we'll consider cases where phi 0 is 0. For instance, if we consider a holographic superconductor, which is spontaneous breaking of the U1 symmetry, so there's no source here. And in the case, as I said, the dimension will be less than 3. And in fact, most of my talk will be focusing on delta equal 2, just for numerical purposes, because then the fall off is still an integer power near the boundary. Close to the boundary also, this function f, let me turn this off.
Sorry to interrupt. If I understand correctly, you're generalizing with the relevant operator, not an ADS black hole, but more like a black brane, because you've changed symmetry from the rotational symmetric to translational symmetry on the boundary.
Sorry, I didn't get the first part of your question.
You've changed the symmetry of the boundary from a sphere, rotational symmetry, to a plane, planar symmetry.
Yes.
So what you're generalizing with this relevant operator is a kind of black brane rather than the ADS black hole that you started with.
That's right. Yeah, I'll be considering. Yes, that's right. This will also happen. The things I will discuss will also occur for spherical black holes. Actually, there was a paper, I think, a couple of months back that discussed our setup for spherical black holes. But indeed, ours is more like a black brane. That's right. Yeah, so close to the boundary, this function f approaches 1. So in particular, in the exterior, this function f will be positive, and then in the interior, in between horizons or in the interior, will be negative. That will also be important. All right. So I think I said already that we'll mostly consider time independent and homogeneous deformations. And I think that's also, you can see that from this particular metric ansatz. As a disclaimer, I also want to say that we're not considering any stringy or quantum corrections in the bulk. But there will be large curvatures or largest curvatures. And so mostly the statements I will make are at large n and large at hoofdkoppeling in the dual gates theory. All right. Any more questions before I move on to discussing the first case? All right. Okay. So the first case I want to consider are just neutral scalars in the presence of a charged black hole background. Now, just to get everybody on the same page again, here's the undeformed geometry is the Einstein-Rosen black hole, and here's the Penrose diagram, and the geometry here in purple has a Cauchy horizon. And of course, as I told you, this Einstein-Rosen black hole is non-generic, and we would like now to study what happens when a non-trivial scalar field is present. All right, so let me first give you an argument why the Cauchy horizon gets removed. So in this case, what I want to consider is the mass squared negative, and in that case, we can prove rather easily that the inner horizon cannot be there, and I'll prove that by means of a contradiction. So consider there's two horizons. And so there's an outer horizon and there's an inner horizon. Then I can construct this quantity. And so this is just a total derivative. And knowing that f vanishes on both horizons, we have this first equality. And this particular total derivative here, using the equations of motion, I can rather easily write that in terms of this object. So this term is positive, but if we now look at this object in square brackets, then we see that it's negative. Phi square, we can always, the scalar is real. If there's no charge, we can always choose a gauge where this phi is real. Then this phi square is positive, m square is negative. We're in between two horizons, so f is also negative, and then this derivative phi square is also positive. So this quantity in square brackets is negative or zero, and this has to, of course, equal zero. So this would only work if the scalar field is absent, or we can't have two horizons, an inner and outer horizon, in the presence of the scalar field. And so what this shows is that the inner horizon, here is the in, gets removed by the presence of this scalar field. And yeah, so for these relevant perturbations, very easy to see that that the Cauchy horizon is gone. And as Juan was asking about irrelevant perturbations, so here for m squared positive, the Cauchy horizon can be there, but it's sort of in a non-generic fashion, because for any fixed mass squared, it only exists for a very particular temperature. And so there's a discrete set of temperatures if you choose the mass, there's a fixed temperature for which this Cauchy horizon will be there. And of course, that is again rather fine-tuned. So that's a very special point again. So these are again non-generic. So these also special solutions. All right. So if we don't have the Cauchy horizon, then the question is, okay, what happens to the geometry instead? Like what type of dynamics happens in the interior instead of this instead of the Cauchy horizon? And what happens is what I plotted here in this plot. Is that the would-be Cauchy horizon, the GTT component of the metric, changes very abruptly. And this is especially pronounced when the scalar field is very small. So when the source on the boundary is very small, the effect is more dramatic. And so here you can see this is a log plot. So log GTT is plotted here. And you can see that it goes from approximately sort of linear, as we will see in a moment, I'll explain that, to an exponential decay. And what that means at GTT basically is the GTT measures the length of the Einstein-Rosen bridge. And so if I compute a finite stretch of the Einstein-Rosen bridge, it will go exponentially fast to zero. And so this is why we call this the collapse of the Einstein-Rosen bridge. And we can actually also do this analytically. And so the equations that we're solving are rather complicated. They're coupled ODEs. So you might think that, oh, that's all simple and maybe you can, but they're very intricate and they show some interesting behavior. But to get some analytic handle on them, what we did is we basically from the numerics, we looked at certain terms in the equations of motion, and we saw that certain terms are small. And then we use that as input into an analytic analysis of dropping certain terms in the equations of motion, and in that way obtain an equation or a differential equation that we could solve analytically. And in particular, in this ER bridge collapse in the regime just in the interior, and so this is just slightly in the interior here, normalized. Horizon is at 1 here, and so this is only slightly in the interior. It's very, you can see numerically that you can disregard you can neglect the mass term and the charge term in the Maxwell equation. And that gave us an analytic handle on the equations of motion. And so let me just quickly, briefly just mention how that worked. So we're probably considering a small boundary source. And another small parameter in the game is the distance from the would-be horizon. So that I call that ZI, the would-be inner horizon. And by applying the approximations I just mentioned, there's a simple differential equation for the GTT component of the metric, whose solution is simply given by this. And so there's some integration constants, C1 square and C2 square, and then there's here this equation that governs the dynamics of GTT. And these C1 and C2 are related in this way to the boundary source. And so C2 over C1 is approximately 1 over the boundary source, and that is getting large. And so C2 over C1 is getting large. And then there's 2 regimes that you can distinguish. It's either delta Z smaller than 0, so that's just before the inner horizon, and then just after the would-be inner horizon. So in the delta Z smaller than 0 regime, the geometry just basically looks like Reissner-Nordstrom and has a linear decay towards 0. but at large, and so this follows here from basically neglecting this logarithm compared to the GTT. And but on the other hand, if delta C is larger than 0, then this thing will be negative, and then you can neglect this GTT component, this term here, and you get that GTT is exponentially small. And so it goes from the linear behavior to an exponentially small behavior. And for the scalar field, similarly, the scalar field derivative has this particular behavior. So you would think that it's becoming large because delta Z is getting small, but actually because this C1 over C2 is also becoming very small, this derivative on this side of the collapse, so delta C smaller than 0, is actually, this term is not that big. It is only on the other side of the collapse, so delta C positive, where the derivative is becoming large. And so schematically, just to the collapse is if this is a finite stretch of the Einstein-Rosen bridge, it gets exponentially smaller in the other regime after the collapse. Okay, so that is sort of how we could analytically track the behavior of GTT by ignoring certain terms in the equations of motion, and gives a very good fit to the data that we obtained numerically. And so the red curve here is a numerical fit using this function here to the actual numerically obtained result that's given in blue. And so that's one way to understand the behavior, this crossover behavior. Now after, okay, let's see, this is not right. Okay, so now we are past the Einstein-Rosen bridge collapse, and after this, the geometry asymptotes to the Kasner universe. The Kasner universe basically as follows. So the scalar field has a logarithmic behavior, and these chi and f functions. So chi has also a logarithmic behavior, and then the e to the minus chi will have a power law behavior, and the function f will also have a power law behavior. And to ensure a smooth solution, so not a singular solution, this alpha parameter here, this coefficient of the log, needs to be bigger than 1, and it's to ensure that the flux terms are unimportant asymptotically.
Sorry, could you say again what it means to be after the ER collapse?
Yeah, so after the E.
What distinguishes that regime from the next regime we're going to study?
So in this case, the metric is exponentially small, and the scalar field.
Is it singular? Is the geometry singular?
No, this geometry is not singular, but there's large curvatures. There's large curvatures, but they're not. Okay. Yeah, they don't blow up. Okay. Yeah.
This gets cut off when the Einstein-Rosen bridge is exponentially short, or when does it?
You mean when the curvature gets large?
Well, you have the regime of collapse. I was wondering, you're going to tell us what happens next, but I was wondering where's the transition between the two?
Yeah, the transition between the two. So the scalar field has a particular behavior, so its derivative can become large, and then after that collapse, it settles on a logarithmic behavior, yeah, so there is a crossover regime where it goes to a logarithm. And later in some other examples that when there's a charged scalar, we will see that settling a little bit more clearly. But yeah, here there's also a behavior where this the scalar field or the GTT component of the metric again goes to a particular power law behavior. Yeah, so this doesn't continue all the way. Like there's a behavior this exponentially decay stops at a certain point, and then it goes over to a power law behavior.
Can we think of this as sort of an FRW universe where one component dominates versus another component dominating?
Exactly. Exactly.
Which are the components that dominate in each?
Yeah. So I was about to get to that.
Okay. Sorry. Yeah. Maybe.
Yeah.
Can't wait till you get to it.
Yeah. I'll get to that now. So yeah, two things that from this asymptotic behavior is what I would like you to take home is so this alpha parameter needs to be bigger than 1 for these flux terms to be unimportant. And the fact that here we have a logarithm, so the scalar field actually blows up. And this goes back to what I was saying before, is that, okay, the interior is unstable because close to the singularity, there's actually a blow up of the scalar field profile. So this geometry asymptotes to what is known as a Kasner universe, and a Kasner universe is in the case that we will consider with the planar topology, has the following form. And so the metric can be brought in this form, and where tau is now the time-like coordinate inside, and tau is 0 refers to the singularity. And the scalar field has this particular behavior. And so indeed, you can see that whenever these exponents, pt and px, which will be the main players in the game, whether they're positive or negative tells you whether a direction is contracting or expanding. So I think that is what you were referring to, right, Juan?
Yeah, well, yeah, that, and I also was wondering whether which term where the scalar field was dominating, or perhaps the curvature was dominating, or yeah, well, perhaps.
Well, yeah, in this case, the curvature will be large just after the collapse, but then the curvature will just settle on some finite value, so it won't be too big after. But there is a regime where it can be large, yeah. Anyway, so the geometry asymptotically is a Kasner universe with this particular metric, and these exponents pt, px, and p phi are not all independent. And a way of parametrizing them is and so the relations amongst these Kasner exponents. And what we did is we parametrized this with the parameter alpha. So alpha is basically the coefficient of the log of the scalar field, and pt will be given by this formula. And so pt, that's determines the behavior of the GTT component, and because this alpha was bigger than 0, bigger than 1, this pt is between 0 and 1. And so for these particular charged black hole geometries. And just to give you a few examples of known geometries that approach a Kasner universe, for instance, like one geometry is that Schwarzschild ADS, where pt is -1/3, so that would correspond to alpha 0. And then there is also another extreme, which is pt equal to 1, or alpha to infinity, which is a regular inner horizon or a null singularity, or also you can also think about it as a Milne universe. Okay, so that was basically what I wanted to tell you about the neutral scalar with a charged black hole. Yeah, so we saw that there's a collapse of the Einstein-Rosen bridge, and that collapse is followed by a asymptotic approach to a geometry with a particular Kasner form. Now, what I would like to do, are there any more questions about this before I move on?
Yeah, I had a question on what do these constraints mean? How do they arise, these constraints between the PI?
Oh, they arise just from the equations of motion to have a solution to the Einstein equations.
Okay.
Yeah.
Is PX positive as well? Or is PX negative?
Well, if PT is between 0 and 1, then I guess PX can be negative from this relation. Yeah, the constraint is that PT is between 0 and 1, and then from this relation you can see that PX can be negative, yeah. Okay.
Can you comment why PY equals PX and when that might not be true?
Yeah, so that we chose here a homogeneous background with a planar topology. And so in that case, the PX and PY are the same. If you have a boundary, if you have a deformation of the boundary where there's an inhomogeneous deformation, then there could be also a PY in principle. Yeah. All right. Let me move on to charged scalars and charged black holes. So the setup will just be similar as before. First, I will tell you a little bit about why there's no Cauchy horizon. All right. So if you look at the solution and you if you look at the equations of motion and you try to find a solution by perturbing around, say you start with the solution at the horizon, and you expand the solution, make some power series ansatz, and what you find is that you would have both. You would have either if you do that series expansion, and you start at the 0 of this f, and say now there's 2 zeros, then what you find is to have this power series, so real analytic solution, is that the scalar field or the gauge potential must vanish on both horizons. So either the scalar field has to be 0 on the horizon, if that is the case, then you can show that the scalar field has to be 0 everywhere. So that case we exclude because, okay, we want a non-zero scalar profile. And if we have a non-zero scalar profile, then the gauge potential needs to be non-zero, needs to vanish on both horizons. And I will now show that that cannot happen. So the gauge potential cannot vanish on both horizons if both horizons are present. And so the argument is against simple. You can construct a quantity Q here, which is basically a conserved quantity by rescaling, doing certain rescalings of the action. You can find that the action is invariant under certain rescaling of the coordinates and the fields. And the conserved charge is Q, and it takes this particular form. And so, and this big phi here is the gauge potential AT. And indeed, if the derivative of this Q object is 0, and the derivative here means a z derivative, so a radial derivative, or in the interior will be a derivative in a time-like direction. You can show that these two things need to agree on the horizons. Since I assumed that the gauge potential vanishes on both horizons, I end up with an expression like this. And you can see here that since f prime, so that's the derivative of the function f, that will be negative for the outer horizon, but positive for the inner horizon. And since these other two quantities are just positive, this equality can never hold. So you get a contradiction that you cannot have these gauge potentials to vanish on both horizons. So that excludes the possibility of having an inner horizon, similar to the case that we studied before, but here it will just never occur. Basically, there's in this charged black hole for the charged scalar, there's two cases that you can distinguish. Either you look at the spontaneous case or the sourced case. And so the sourced case would be there's a non-trivial source turned on for the scalar field. But the more interesting case that we will be focusing on is the spontaneous case, where there's a non-zero VEF for the dual operator, but the source is zero. And so this, in the dual side, in the field theory side, this is a phase of matter that's the holographic superconductor. And on the bulk side, this is reflected by the fact that if there can be a lump of matter a lump of scalar charged matter in the bulk that is stabilized by the gravitational pull and the electric repulsion from the horizon. And so there's a lump of scalar field in the interior, but the source on the boundary is zero. And in that case, the interior is a lot more intricate, and it consists of at least two epochs. And these two epochs, so here, this is again the regime where there's the Einstein-Rosen bridge collapse. So you see, let me just first tell you what these different plots are. So this is this logarithmic derivative of GTT. Then the scalar field derivative is plotted in orange, and the logarithm of GTT is plotted in blue. This first part of the geometry here, this is what's known as what I discussed before, Einstein-Rosen bridge collapse. And so basically the same analysis as we did before in the neutral case also goes through there. But then the geometry enters in a phase here, basically all the way here, which is a regime where the scalar field oscillates. And the scalar field oscillates in a way very similar to what we know from Josephson oscillations. Because in Josephson oscillations, if you apply a electric field on or just a potential over the superconductor, there's a current that is flowing and that will oscillate because of there's some phase winding in the background. The oscillations here of the scalar field depend precisely in the same way on that phase winding. And so basically what happens is that the scalar field, yeah, I don't want to write that down, but the scalar field has oscillations that depend on the phase winding. And so that's why we dubbed this regime here the Josephson oscillations. And in this regime, what you can do to solve this more analytically is ignore the mass term as we've done before, ignore the charge terms in the Maxwell equation. And furthermore, you can also ignore the cosmological constant in this regime. And then what you find is that the scalar field will have a behavior. I'm just going to draw this, or write this more schematically, just for later purposes. So there's going to be some constants, some unknown constants. But the scalar field will basically behave like a Bessel function, J0, with argument some constant over z square. So when z is small, there's many oscillations, and so those are the oscillations that we see here. And of course, because they're not pure sinusoidal oscillations, they back react on the geometry, and they create this imprint of very fine oscillations also on the metric components. Notice here that you need to take some derivative to see that. Here in the GTT itself, you don't see it that clearly. And so the scalar field has these oscillations of Bessel type. And when the argument of the Bessel function becomes small, or when z is becoming large, at this, so z much bigger than 1, the small argument expansion of the Bessel function is a logarithm. And so this will be some other number times log of z. And so here you see sort of the transition happening from this oscillatory behavior to a logarithmic behavior, and so to a Kasner regime.
What is the proper time along this? So C seems to increase forever. What does the proper time do? Is it finite?
Yeah, and it's very small.
Okay.
Yeah, indeed. Yeah, so Z here is a bit of a, was a handy coordinate to use. But yeah, the proper time is very small and finite. Yeah. All right. Okay, so that's what happens to the scalar field, and the yeah, I think that's all I wanted to say here. Yeah. So notice what I want to draw your attention to is that this geometry was very close to criticality. So the temperature is very close to criticality, but it's this geometry, the interior, depends very sensitively on the temperature, because if I change the temperature just by 1,000, you see that the geometry already changes quite a bit. And so maybe I should have said that this behavior just continues forever. There's no change. And the reason for that is that the PT here is bigger than 0. And so it's not very clear from the plot, but trust me, the PT here is bigger than 0. But if I change the temperature only very, very, very slightly, there's actually a new regime that pops up. And so this regime and this regime is what we knew before, and that's what I told you already. But then here there's a new regime, and you see that there's again a sort of an inversion happening, and the reason for that is that here, by changing this temperature very slightly, this PT in the intermediate regime is negative. And PT being negative means that this parameter alpha will be less than 1. And so that means that in this interior part of the geometry, the flux terms are important. And that is imprinted also by the fact that GTT here is growing. and it grows very, very slowly. Again, proper time is very small, but it grows very, very slowly. But at a certain point, the GTT has grown so much that the back reaction is significant, and the geometry changes in this regime. And so the flux terms being important cannot continue all the way asymptotically. There has to be a transition period where the flux terms again become small. And so that means that this PT being negative will go over in this regime to something positive. And when it is positive, it will just continue forever and approach the singularity. Yeah, and that inversion that happens here, we call that a Kasner inversion, and because these Kasner exponents get mapped just before and just after this regime get mapped to each other in this way. And that is again something that you can analyze analytically by again ignoring certain terms in the equations of motion. Basically, what you're solving is a massless scalar field in flat space, and that you can show has a particular behavior like that. Right. So if PT is negative, it has to transition to something that's positive, and then it continues on forever. Notice also that this transition is nonlinear because the derivative of the scalar gets inverted. Okay, so I told you that there's a very sensitive dependence on the temperature. So let me show you what happens when we study this Kasner exponent PT as a function of the temperature. And so then you get this pretty amazing plot that I think is still very, very, very interesting. And so here what I've done is I plotted PT, this Kasner exponent, as a function of the temperature between 0 and the critical temperature. And what I want you to focus on is this regime, so very close to the critical temperature. Ignore this regime for now, that's not important. But here, very close to the critical temperature, you see a buildup of many oscillations in this function P, in the Kasner exponent PT as a function of temperature. And so actually what you can show is that there's an infinite number of oscillations. Basically, if we go back a little bit here, you can show that this coefficient here that determines the Kasner exponent has a behavior that goes like this: 1 over T over TC plus C. And so you see here, because of this inverse powers, there will be infinite number of oscillations as you approach TC. So yeah, that you can look at analytically and find that behavior, match it with numerics.
So here, critical temperature is defined to be where this behavior happens, or is it related to critical temperature in the terms of superconductors?
It's the second, yeah, it's related to the temperature of the superconductor. Okay. Yeah, that's right, yeah. Yeah, so it depends sensitively on the charge and the mass of the scalar.
Okay, so when you approach the critical temperature, the wave of the scalar becomes very small?
Yes, yes, yes. No. Yeah, so right. So very close to this critical temperature, there's an infinite number of oscillations. And what I plotted here, just to zoom in a little bit more, here is some gray dashed line and a black curve. And so this gray dashed line is the intermediate value of the Kasner exponent, whereas the black line is after the inversion. And so it's just whether I plot this guy or this guy. This guy is the gray dashed line, and this is the black solid line. And so in the intermediate region, that can become negative, and then we know it can invert to these to positive values, and it does so in an infinite number of times as we approach TC. But something interesting also is what happens down here. And so down here, the inversion would tell us that this point, minus a third, gets mapped to 1. But the PT equal to 1 means that there's a regular inner horizon. And I just argued for you that we can't have such irregular inner horizons for these geometries if the scalar field is present. So that option seems to be excluded. Very close to alpha is for PT is minus a third, the geometry just goes back to regular inner horizon. And what happens is that some of the terms that we've ignored in the equations of motion actually become important when alpha is very small and PT is close to minus a third. So when alpha is not too small, the charge terms are not so important. And then I mean just all the charge terms. And so in describing this behavior and the inversion and we dropped all the charge terms. But you can show by just plotting the numerical solutions. It's a bit complicated, but it can be done. Is that the charge terms are becoming important again when PT gets really, really close to minus a third. When alpha, so I'm using alpha and PT interchangeably. Let me put maybe in blue here. So PT was alpha squared minus 1 over 3 plus alpha squared. So when alpha gets really, really small, and hence 1 over alpha very large, the inversion is basically alpha to 1 over alpha. Charge terms are important again, and the inversion get actually modified. It basically cuts off the value of alpha after the inversion. And in particular, what you can see here, so here I've plotted such a situation where alpha gets really, really small. So in all these cases, so this is here I zoomed in on the inversion, and you could see that this is slightly different from what I showed you before. But when alpha gets really, really small, so here the value of alpha is very small, then charge terms become important. And you see here, so the gray dashed line here below is sort of what we saw before. There's alpha to 1 over alpha. But when alpha continues to become smaller and smaller, the inversion gets different. And it even gets so different that it can oscillate again. So that's more clearly happening in this picture, in this plot. And now really something interesting happens, is because you see that at every inversion, the scalar field can oscillate again. That means that that if PT was negative in this region, that there's an inversion, then even after the inversion, the Kasner exponent PT can still be negative. And I think here you can see one example. I think it's one of these curves that has again a negative value for this PT. But that means that there has to be another inversion at some larger value for Z again. And also at that inversion, there can also be another very, very precise temperature where there's again a negative value for PT. And so what happens here is that when you tune the temperature very, very sensitively, very, very accurately, you could end up with many, many of these inversions. And even there's a discrete number of temperatures actually where where there can be an infinite number, or basically you can get as many oscillations as or many of these inversions as you want. And so this is almost like a fractal behavior, because whenever you get close to PT is minus a third, there's a second inversion happening, but then there could also be even more of these inversions happening. And all of that happens very, very closely to PT is minus a third. So even though these oscillations here are already like pretty novel and rather remarkable, even on top of that, there is for every time this black curve is close to zero, there's again and sort of if you zoom in into that regime, there will again be, if you look at these there will be multiple inversions happening. And so that's the advertised fractal behavior that I was mentioning before. So I think that's a pretty cool feature of the black hole interior that we didn't anticipate, and I think is very, very, very interesting. Okay, that's all I said. Yeah, so basically then just to conclude, I think black hole interiors are very rich. We saw just for some simple matter choices that for instance, there's a phenomenon that I call the Einstein-Rosen bridge collapse, followed by a Kasner universe, or even a more intricate behavior with Josephson oscillations, and then these Kasner inversions and fractal behavior. So there's a wealth of interesting things happening on the interior, but the exterior, while on the other hand, the exterior remains rather mundane in that sense. And yeah, that's all related to the very high sensitivity of the exponent PT on the boundary data. So especially the temperature, very sensitive on the temperature. Right, I think I'm over time already. Let me stop here. Thank you.
Thank you, Jorrit. So questions that we haven't asked already?
Yes, people have discussed that generically we expect this so-called BFKL behavior near black hole singularities.
Mm-hmm.
This is a special case of that, where there are no spatial gradients.
Yeah, that approach to the singularity is slightly different from ours, because first is the charge was really important for the behavior close to the singularity. Whereas for those BFKL type singularities, it's there's even such behavior without any charge terms. So these are, I think, a bit slightly different than the usual ones. That like it was the charge. Sorry, let's see. It was these type of oscillations in the scalar field that sort of gave these extra sort of fractal type behavior close to the singularity. Whereas I think in BFKL it's sort of slightly different how that fractal behavior or the chaotic behavior occurs. But maybe there's a similarity, more similarities, yeah.
Okay, thank you.
Anyone else? I had a small question. How different would it be if you had a 5-4 coupling?
Yeah, that's very interesting. So if there's a 5⁴ coupling, then let's see. If we have charged scalars, then you would still this proof here would still go through. But if you have a neutral scalar, so let me go back. So here a neutral scalar, then basically this term will change into something like phi v prime phi. It needs to be negative. And so by tuning a particular, tuning the coupling of that 5⁴ to be positive or negative, you can have a similar proof as this. But the more intricate, so that's just the Cauchy horizon problem. But the more, what happens to this Einstein-Rosen bridge collapse? Like all these regimes are highly nonlinear and sort of intricate behavior going on, and so they're probably like affected by that scalar field potential, and they change. You could change significantly.
But the negative sign here, you don't have a BF bound to appeal to, so a negative sign would destabilize, no?
Yeah, that could be. I'm not. We didn't really study that in detail. If the scalar is interacting. But I guess that would be very interesting to see. Also, because more generally, these couplings would occur if you study some compactification.
More questions? So for the irrelevant operator, you said that the Cauchy horizon was non-generic. Is that obvious from what you said, or is it some further argument?
No, it's pretty elaborate to show that, and you need to. Let's see how that went again. I think when the mass square is positive, then solving the equations of motion, requiring that there's two zeros in f, in the function f, basically amounted to solving a certain Sturm-Liouville problem. And that gave you like a discrete set of eigenvalues. And then from that, you could deduce that only for certain special temperatures, for a given mass square, a Cauchy horizon could exist.
Okay.
That's
I'm not sure if are there more questions now. If not, we'll thank Jorrit again, and some of us will reconvene at 4.